Okay, 5.4 bank curves one more time because I've had a concussion recently and I couldn't explain the trigonometric proof. But here we go. So, the problem with flat curves. Let's draw a flat curve over here. And what happens when a car goes here? As explained in the previous video, when the owner turns the tires from this configuration to like this configuration, and let me like draw like a tick here so we understand how it's rotating. And we turn it this way, meaning the car rotated like 30 degrees or 45 degrees to the left. Then a normal force acts, or a friction force acts here, which we'll denote as FF. But that has to overpower the force of the car that is barreling towards this way. And that would be considered Fy, I guess, in this case. But what happens if Fy overpowers Ff? That means there's nothing that is stopping the car from accelerating completely forward this way, or I mean, I guess the net vector here, this way, and just going off the road. So that's really dangerous for a few reasons. And let's define what FF is. And the friction force, remember, is the static coefficient force. Well, I mean, depends, static or kinetic. And this is static, and I'll explain for a second, even though the car is barreling. And the Fn, which would just be mg, under normal conditions, obviously. But or under a regular plane. But the thing here is that this just depends on the make of the car or the plane, so it doesn't really matter. This is completely dependent on your situation. But this one is the killer because ice has a very low static coefficient friction, which means that it will apply a very, very, very small friction force, and as a result, it won't be able to overpower the vertical force of the car, which throws the car this way. So quite genius. And the reason why kinetic coefficient friction force is this, well, like if people step this way, you're only touching one point of the ground here. And technically, you're not pushing, which kinetic friction force is pushing against the surface. Here you're pushing a box and that surface is in contact the entire time. Here it's only in contact on one point. And similarly with the car, you're only touching, like, let's say this part of the wheel, then it gets to this part of the wheel, then it gets to this part of the wheel. It's only being touched really at one point exactly, and that's rotating over and over. But in this case, you're only touching one point, and that's why it's called the coefficient static friction force. Ingenious. So now we're gonna explain the proof, and first let's and that's the danger of flat curves. I mean, relying on one force is also quite dangerous because you're putting your eggs all in one basket. If it snows, then the ground is no longer under the static coefficient friction force that you thought it was with the pavement. Now it's snow, and that has a lower coefficient. So what is a Banks curve? And I'm not even going to try to explain it. I'm not going to try to draw it. I'm just going to show you what this is. This is what it looks like. It's just a triangle. It's just a plane rotated 90 degree or theta degrees here. It would be. So let's do the proof here. And this is quite genius. So listen here. So I'm not going to draw the car because I'm not good at drawing. Instead, I'll draw a box in place of the car. So remember, and we'll draw this way. Actually, let me just make it a little bit longer. Remember that the normal force is always perpendicular, so this is 90 degrees, which means that this would be beta degrees, which beta is just 90 minus theta. So it's just a constant placeholder here. Now we cut this into a triangle straight down, which would be the force of gravity, or weight, I would say. And I'm just going to use W so it makes it a little bit easier to understand. But I'm going to draw a line so it doesn't convolute anything here, or concentrate the amount of variables that are already existing within this plane. And we'll do 90 degrees here and 90 degrees here, which is quite self-explanatory. So if we do the math, 90 plus beta plus c is equal to 180. And here, 90 plus theta plus, and if this is c here, then this would be 90 minus c, because 90 minus c is equal to 180. I guess we can use a sort of Gaussian elimination here, but I'm not going to. Instead, we realize that C or B is also 90 minus C. So in reality, this is written as 90 plus theta plus b. And the reason why b is 90 minus c is because these have to make up 90. So it's the same as b plus c equals 90, and then just subtract c on both sides. So sorry, 90 plus theta plus b is equal to 180. And then here 90 plus beta plus c is equal to 180. We'll just subtract 90s on both sides, which means that c and theta must equal the same thing. And that was a pretty geometric proof, or I guess trigonometric proof, but that was quite self-explanatory, but I just wanted to explain it anyways. So in simple terms, we can simplify this triangle into 90b plus theta, and then b here. So these are similar right triangles. Now, I'm going to draw this up here because remember Newton's third law, every reaction has an equal and opposite reaction. Every action has an equal and opposite reaction. So that means there's a normal force that this plane is exerting up on here as well. And since these two are parallel, this will be 180. So 180 equals beta plus theta plus this 90 degrees here, which is the same thing as 90 equals beta plus theta, which is self-explanatory as well. And I'm going to draw this upwards here. And I mean, I'm not even going to try to explain it because you should have learned in geometry that this would also be theta. So now we have a triangle, which is theta. This would be Fn. Wait. Sorry, this would be Fn. I read it wrong because that didn't look right. So Fn sine theta is equal to the centripetal force, and Fn cosine theta is equal to the forwards force, and the ratio of the two becomes Fn sine theta over Fn cosine theta is equal to, and we're just establishing a ratio. So if this is the centripetal force that is keeping it within the curve and making sure that it doesn't fly off, then it would be mb squared over r, which is simply just a formula, so you're not really changing anything. It's just the same exact thing. Fn cosine theta would be mass times gravity because it's perpendicular to here. Let me think. Yes, because this is the normal force cosine theta is always just going to be mass times gravity. So that's logical here. So we just do some simple things. So that means tan theta, or simple algebraic manipulation, you just cancel Fn on the bottom and top, m on the top and bottom, equals v squared over rg. If you want to solve for velocity, you can do rg tan theta square root equals velocity. And you don't have to plus or minus because velocity, I mean, I guess velocity could be negative here. But we know that this is a centripetal force and we're only dealing with magnitude, so it'll be positive. So what does this velocity give us? And now this velocity gives us the perfect ratio in which the centripetal force can act opposing to the downwards force. And that means this velocity will make sure that on a frictionless banked curve, the car can go smoothly around even if there's no friction present. However, in such case, slower, faster velocity will lead to the car going down the curve because the ratio is not the same. So yes, because it wouldn't be the same here because the velocity forward would not be the same. So that's the logic here. Something with the smaller magnitude will lead to the mass times gravity overpowering. So make sure that this ratio is intact. So basically this velocity ensures that the car has a perfect centripetal force that doesn't need friction to act against it, which basically eliminates the need for ice. But I guess ice would affect it if ice fell on this banked curve. But yeah, that's the simple logic between 5.4. So